Welcome everybody to this session in the Mind Grid. Today we're talking about FPGA and its role in machine learning. So this is a relevant study because we want to see how the FPGA plays in this ecosystem of machine learning neural nets where GPUs and CPUs have traditionally been used. Um, so with that backdrop, let's dive into how this all works out. So this is a neural net, and neural net is just one kind of machine learning algorithm. In a neural net, which is modeled around the concept of a neuron, and a neuron is essentially um, a concept in which you get a whole bunch of inputs coming in, and these inputs can be called, let's say, I0 to IN, and then you have weights on each of these inputs, W0 to WN, and then you have a bias for this neuron. And then what you do is basically you sum, so it's a sigma over I j wj plus b, and this is your output, right? And then there is some activation on it, etc., which we don't go into at this point. But needless to say, what happens here is that any one of these neurons, and these are special neurons because these are input neurons, and there might be special output neurons which get a little bit of special treatment. But let's look at these middle neurons, which all of them pretty much look alike because all they're doing is basically this equation, which is, a sigma or inputs and multiplied by weights plus a bias. And that's the bread and butter, the core function of these neurons. So very simply put, if you look at this, this is just multiply and accumulate, multiply and accumulate. That's kind of all that this neuron's main function is. And so neural net essentially is boiling down to doing these functions efficiently. And if you look at modern GPUs have very high amount of floating point operations per second, gigaflops. Even some of the latest, the GPUs are measured in teraflops. They're no longer measured in gigaflops. So they are massive, massive in terms of their processing capabilities, and they can crunch so many floating point operations in terms of their arithmetic logical units. They are extremely, extremely powerful. The other thing is that the GPUs have evolved to do a whole lot of parallelism, right? And the more parallelism you can handle, the more powerful the GPU. So those are kind of the core competencies of GPUs, but we know that there's high power consumption in these GPUs, and that's kind of the Achilles heel of the GPU, and which is where the FPGA might be able to find, its place in that ecosystem is by doing things in a slightly more power efficient way. So we will dive deeper into this topic to see what GPU is and how it's operating, and then what the FPGA would do. So GPU is a graphics processor unit. It evolved because of the need of, doing like vector processing or whatever. The computations that happen to display something on the screen is very repetitive. Like in the games or something, if you're trying to plot, you have to plot, the movements, the colors, etc., the shading, all that you have to do to get very real looking graphics. It has to be done extremely, extremely fast, and millions of operations, billions of operations per second. So that's why these graphics processor units have evolved in such a way. Their structure kind of looks like a CPU. You have access to an external memory, you have your memory controller, so data can flow towards your cores. In a normal CPU, you would have cores, a whole bunch of these cores, 8, 16, 32 cores or something inside a CPU. And then you would have a bunch of caches, right? You have L1 cache, and then you have, L2 cache, L3 cache before your memory controller, right? And you would have external memory. But these cores are all, um, kind of at the equal footing, right? They all have access to L1 cache, and then they have these external caches, and then they access to the DDR. So they're all equally powerful. In case of a GPU, which is based on a slightly different idea, the idea is crunching numbers in a very high volume. So they have these specialized cores, right? And these cores are inside what they call as a streaming multiprocessor. And these cores, whole sets of these cores, right, are behind an L1 cache. Um, and so the difference being that it's almost like if you clubbed a whole bunch of these cores together and gave them a common L1 cache, rather than each having their own L1 cache. If you just like club these and give them one L1 cache, that's kind of the concept, but at a much larger scale. The other difference is that each of these cores that are there in this GPU are capable of doing lots of threads, thousands of threads, um, and that makes these cores a little bit different from a traditional CPU core because they're designed for massive parallel multi-threading. So combine all these things together, a common L1 cache to whole bunches of these processing cores, and then the fact that there is the special construct of SIMT, which is single instruction, multiple threads. And what happens in this case is that when you load some work that you have to do, it's a single instruction, but it may have lots of data. And then you can enable whole bunches of these cores on this streaming multiprocessor. And then all these cores start crunching on this instruction, a single instruction that you have pulled. So this makes it extremely efficient use of the L1 cache. Um, and because these instructions, all these threads are, I mean, thousands of these threads are basically using this L1 cache so effectively, there's less cache misses and the performance is very high. And so this idea of SIMT is very powerful, and would, we would do well to learn from it. So keep that in mind. This SIMT is a great idea. Um, when you pull a bunch of data from external memory, you should do all you can to make sure that you utilize all of that data without doing any more lookups, and do as much processing in parallel as you can. And so that all work has been done. Now, the other thing is these cores are specialized. Like I said, differentiation from CPU is that they do not have as much control logic. Like they may not be specialized enough like a general purpose CPU core. They may be lacking branch prediction. They may be lacking a whole bunch of control logic, which is there in a common CPU, right? An advanced common CPU. All those things are missing, but they are not into all that stuff. So they are mostly into number crunching. And so they may be okay doing this. I mean, the GPU cores are specializing at just crunching arithmetic operations that are basically repetitive, and they have to be done for whole bunches of pixels and so on. So this whole GPU concept is basically excelling at the massive multi-threading and to be able to compute all these pixels in parallel at the same time. As long as the pixels have some common theme, they can be clubbed together and a whole bunches of threads can be run in parallel, and they can compute all those operations at the same time. So that is the general concept of a GPU. Now, how can we implement this concept in FPGA? It is so much, it's so interesting that an FPGA, essentially, if you look at an FPGA in this form, the FPGA has an external memory access, right? It has these inputs that are coming in from the outside, and it can do all the same things. You could create basically the equivalent of that SIMT core. You can have a whole bunches of those parallel engines implemented here, and you may even put some, SRAM to store the data into these and create the exact same structure. You could create a streaming processor of your own inside this FPGA. Now, the one difference I would say you have more control over in the FPGA because you don't have to implement all the floating point operations, right? Even though the GPUs have this flops, the excessive compute capability, You don't have to do floating point. You can do fixed point. You can do optimized fixed point operations, right? And so you could do some smaller, more scaled down version of an ALU here, and thus saving tremendous amount of power doing the same things because you know that you can do it in a lot less. So those capabilities exist, but you can essentially copy an SIMT core right here and put some cache in front of it, which is a block RAM inside. And FPGAs these days have lots of block RAM. So you might be able to cook up some caches here and some caches along the way to the memory. And that way you can build your SIMT engine right there, right? But we can go one step further. So the other concept is that if you optimize your weights and biases, the weights and biases, as a reminder, if you look at a node, it has these inputs that are coming in, right? These inputs, and they're multiplied by weights here on these branches, and then there's a bias, and that creates the output. So these weights and biases, if you could store for all the thousands and thousands of neural net nodes that are there, if you could store them here inside the internal SRAM on chip, this is almost, SRAM is like a cache, right? So if you could store your weights, your biases on the cache itself, you don't have to go to the external memory. All the latency of going to an external memory and the parallelization that you have to think of is gone. It's so simple to just pull the data straight in right into the SRAM and just keep reading and computing, crunching. That capability also is available to you in an FPGA. If you choose to design it in such a way, then you have that access from an SRAM directly. And so when the inputs come in, you essentially crunch this input by fetching from the SRAM and then crunching all these, and then you may have to repeat because neural net may have different layers, right? So you process this layer, and maybe it takes multiple clock cycles to process this layer. Then the outputs are available here, and then basically you may be able to store those outputs or just keep them in flops. And then you crunch this layer, then you crunch this layer, then you crunch, and so on and so forth till you reach the final outputs that are available to you. So in a sense, this is working like an SIMT, right? SIMT core that we saw in the GPU, except that what we are trying to do is optimize it even further. First, we said we would have our ALU to be optimized. Then we said we will optimize our weights themselves so that even though we are using, simpler instructions, we also are using smaller sizes of those instructions so that we can compress even further. So given all those things, we can optimize the FPGA to produce a lot more power efficient implementations of what we saw in a GPU. So some of the things that we see in the market today is, like, if you look at XILINX, which is one of the FPGA vendors, they have created this library called Brevitas. And this is just one of the libraries which allows for quantization schemes that are applicable in these cases. And these quantizations provide, they could be built on top of an existing library, like PyTorch was, like Facebook's implementation, like Google had TensorFlow. So PyTorch, they provided a library that integrates into PyTorch, and then it enables you to do quantization so that your weights and biases are already quantized. And if they're quantized, you could apply them to the FPGA because you trained your model in PyTorch, and then the weights and biases coming out of that model, right? So your model here, it's written in PyTorch. And so let's say you train your model based on some offline data, right? And outcome the weights and biases uh, for all the layers, right? All the n layers, these weights and biases are available to you. Then you go program your inferencing engine um, inside the FPGA, and that's getting these inputs and it's producing the outputs or inferences. So these weights and biases then can be loaded on the inferencing engine, and then they will produce the outcome that you desire. But the point is, you have optimized these weights and biases. Let's say they were 32-bit floating point, and now you've converted them to, let's say, 8-bit floating fixed point. So you have saved, 24 bits per operation, and basically it's 24 times 2 maybe, because you have weights and weights and inputs multiplied together. So it's a lot, huge savings here when you do this operation. And when you do this, you can optimize power and make your implementation more efficient. And you may be able to fit more onto the FPGA depending, right? So those are some of the advantages, and you can see the tools are available. You can Google this Brevitas tool, and you can play with it, and you can just play it in Python, right? Because you don't have to go to the FPGA. You can just try to implement it and see what efficiency. Because sometimes I've seen that the efficiencies coming after these optimizations are only like, less than 2 to 3% points below the full floating point operation. So that's extremely, that's a good trade-off to have if the efficiency is not changed by that much. And if you don't care about that much loss of efficiency, then you're okay going with a fixed point quantization. So that's another thing to consider. And here's an example. You can see that this was written in Torch, but then we integrated this Brevitas library. And when we do this, Brevitas library has given us this quant versions of these linear library or convolutional library 2D. So notice that you have been given these bit width to quantize your weights, right? So weight quantization capabilities are available to you here. And that's tremendous because that will give us small weights. With small weights, we can save a lot of space. We can fit these into an internal SRAM memory. And with that, we'll be able to optimize our neural net to run more efficiently, right? And fit more inside an FPGA's memory. So those are some of the interesting things. Now, here's an example of where XILINX is claiming their XFDNN quantizer, its efficiency. For example, GoogleNet was quantized under a minute, and the 8-bit version of fixed point networks runs to between, within 1 to 3% accuracy of a 32-bit floating point network. So this is fantastic news for us because now we don't have to use floating point. We can use fixed point, and we know that we only have to do multiply and accumulate. So we don't even have to use a full ALU. We don't have to build a full ALU. We can build something very specific inside the FPGA. And that will help us tremendously in building an efficient and optimized version of the neural net. So in summary, when we looked at the GPU and we looked at the FPGA, we find that FPGAs could do pretty much what the GPU is doing. I mean, it depends on the FPGA size. For example, if you take one of the modern FPGAs, which may have like 1 million to 3 million gates, system gates on them, that's great. But what would happen is that you may still not match the largest GPUs that are available today. But the advantages that you may have are that you can optimize what operations you do. You may not be able to do 32-bit floating point that the GPUs are doing, but you may be able to intelligently trim your weights and biases that you have programmed in the neural net. And also doing this, you will save some space and power and efficiency. And then you can fit them inside the SRAM and inside the chip. I like to call this as like a cache. So if you're able to fit this into the cache, into the SRAM, then you have extra advantage that you don't have the latencies and the inefficiencies with respect to the latencies of the external memory. The external memory latencies are gone, right? So that's another advantage. You don't need an external memory. Your power savings also lie there because you don't need an external memory at all, right? So that's another. You may shut it down, or you maybe in low power mode or whatnot. You will save that power as well. So better performance by quantization and all these optimization tricks that we talked about gives us overall some benefits using FPGA. But at the end of all this, I guess we should consider if GPU is the best option for us or if FPGA can do some of the work. FPGAs definitely are more customizable than a GPU. You can do exactly the ALUs that you want. You can build your own SIMT instruction. You can build your own cores and the cache in the cache line in the caches, the L1 cache, L2 cache, etc. You can build them exactly to your specification, and thus achieving better energy efficiency. So that's it for today's video. Thanks for sticking with me, and I hope to see you in another video. If you like this video, please give me a thumbs up and subscribe to my channel. You can leave me comments if there is something you did not understand or did not like. Do leave me some comments, and I'll see you in another video. Thanks a lot, and take care.